Hello everyone, how are you? Welcome to the next lecture of BJT amplifiers. In this lecture, we're going to talk about how we can use these bipolar junction transistors in different configurations in amplifier circuits. So, if you remember your MOS-FET amplifier configuration lectures, right? So, it had three terminals. So we ended up using one of the terminals, ground in between input and the output to make it like a two-port network. Similarly, we're going to use the BJT transistor in a similar way, and we are going to come up with three different configurations. The first configuration is known as common emitter configurations. Over here, right, if you look closely over here, the emitter is common in between input and the output, so that is why it's a common emitter configuration. A common base configuration in which your base is grounded and the base is common in between the input and the output. Similarly, the other one is called as a common collector configuration in which the collector terminal here is grounded and common in between input and the output. So we have three different configurations. This configuration is also known as emitter follower. We will see why it is called as an emitter follower. Essentially, we can use these configurations to develop follower circuits. So we're going to discuss that as well in the lecture today. Okay. So let's start with characterization of a amplifier. We have discussed this topic in detail, so I'm going to be quick over here. We have discussed this thing while discussing the MOS-FET. Before going deeper into the MOS-FET, three MOS-FET configurations, we have discussed this line and the next one in sufficient detail during discussion of the MOS-FET amplifier. So I'm going to be quick over here. Right, so in terms of a generic characterization of the an amplifier circuit, for example, over here, this is an amplifier symbol. You have an input current flowing in, output current flowing out, a load resistance, signal that you want to amplify, and the resistance of that signal, also known as an internal resistance or signal resistance. Right, then we ended up developing these equivalent model of the amplifier. So if we will look inside what is inside this triangle over here, so this is what we are going to see. Okay, so what do we have here is we have a voltage controlled voltage source, right? So this is voltage controlled by VI with a open loop gain. So we can expand this amplifier into this following circuit as well. Now what we are going to do is we are going to solve the circuit. All right, so we discussed that earlier as well. Our input resistance, this input resistance of the amplifier, equals VI and the current that is flowing over here, II, right? So the input resistance is VI over II. The input voltage that is coming over here, the input to the amplifier will be, you can easily find this out by the voltage divider circuit, right? So this VI across Rn will be equals to Rn over the addition of these two resistances and the signal source. So Rn over Rn plus R sig multiplied by the V signal. So similarly, we have seen that the open loop circuit gain or open circuit voltage gain over here will be when our load is not connected. So we can find out our open loop voltage gain as V naught over VI, and RL is infinity, which means that RL is open circuited, so there is no RL. So when there is no RL, if we will find out the output over input, V naught over VI will be equals to the open loop voltage gain. When we will connect the value resistance RL, and we will again find the value of V naught over VI with RL, that will be equal to the voltage gain of an amplifier, the output to the input of an amplifier. And similarly, we will see there is another gain that we defined earlier as well, the overall voltage gain, in which we are interested in seeing what is the output of the amplifier and what is the input signal that we applied. So it's a ratio of the output V naught to V sig. We are going to see its derivation very quickly again. We saw that, for example, how we can find out the output resistance, the R naught. R naught is the resistance that is seen looking back into the amplifier output when Vi is set to 0. So we can also find this out by making this equivalent circuit over here in which Vi is set to 0. So you can easily find out this R naught by Vx over Ix. So we are going to use this concept again in the lecture today to find out the output resistances of the amplifiers. So we discussed all of these things in a lot of detail earlier. Okay, so let's find out the voltage gains. We ended up finding out the voltage gain, open circuit voltage gain for an amplifier when load resistance was not connected. Then we said that, okay, our voltage gain of an amplifier with the resistance, load resistance connected will be equals to V naught over Vi. So let's find out this voltage value over here, V naught, right? So this V naught will be now, we can apply the same voltage divider formula over here. So it is going to be A V naught Vi into RL over RL plus R naught. So if you take this Vi over here, so our V naught over Vi now will be equals to AV naught RL over RL plus R naught. So this is the voltage gain of an amplifier, which is the ratio of the output of an amplifier to the input of an amplifier. Please note that there is a difference in between this Vi signature, which is the voltage that is appearing at the input terminal of an amplifier, to V sig, and the V sig, which is the input signal that we are applying at the amplifier input. All right. So this is the voltage value that we ended up finding. So if you will take this ratio V naught over Vi, the voltage gain of an amplifier can be rewritten as this. Similarly, we can find out another value, which is an overall voltage gain. By now, we have determined the value of the open circuit voltage gain, this AV naught, this AV, voltage gain when load resistance is connected. The third important gain that we want to find out is the overall voltage gain of the circuit, in which our output is going to be this V naught again, and our input is going to be V signal, the signal that we wanted to amplify. So we are interested now in finding the overall voltage gain output to V signal. Okay, so this is the voltage gain that we want to amplify. We can also rewrite this equation as, for example, over here. Okay, so where we are at, we can write this equation GV equals, we did this derivation V signal, so we can call it as V naught over Vi into V naught over Vi into Vi over V signal. So we can write this as a product of these two ratios, right? We already have a ratio of V naught over Vi, so our overall voltage gain is V naught over Vi, which is AV. So we have an AV multiplied by Vi over V sig. Vi over V sig. And Vi over V sig is this equation that we wrote over here. It's a voltage divider at the input of the amplifier. Similar, so we can easily find this out by taking the ratio over here. Vi over V signal is Rn over Rn plus R signal. So we're gonna take this value, put this value over here. So our overall voltage gain is gonna come out to be this. What is AV? AV equals AV naught, RL over RL plus R naught. So AV is this, AV naught, RL plus R naught, and then we have Vi over V sig ratio, which is Rn over Rn plus R sig. All right, so this is our second product. So this is the value of the overall voltage gain. We're going to come back to this equation again during different discussions in the lecture today. Okay. So again, there are three or four important components while characterizing any amplifier: the input resistance of an amplifier, the output resistance of an amplifier, the open circuit voltage the open circuit voltage gain, the voltage gain of an amplifier, this AV, when the load resistance is connected, and finally the overall voltage gain, the output of the amplified circuit to the input signal that we want to amplify, V signal. Okay, so now let's go back to the three configurations. We're going to start with a common emitter configuration. All right, so let's start with the common emitter configuration here. Okay, so here's our common emitter configuration again, right? So this is collector, base, and emitter is grounded, so emitter is common in between input and the output. So this is our common emitter configurations. Rn is the resistance looking into the transistor at the input, and then we have an output resistance Rc. Again, we wanted to use this thing as an amplifier, so we have to flow our collector current through a resistor to make sure that we are converting a transconductance amplifier to a voltage amplifier, and then we are taking the voltage across this resistance Rc. And our resistance R naught is the output resistance that can be seen looking into the output terminal of an amplifier. All right. Now, if you remember the two models that we have discussed earlier, let me show you those two models again. Right, so one model was a hybrid pi model, right, in which over here our emitter was common, and this was our base and our collector, and we were representing the base and emitter by this resistance R pi, and then we have a current source here. You can also convert that into a voltage control current source, a current control current source, depending on the values that we want to use. And we also know this value of R pi, the resistance that we're going to have, which is called as a base resistance over here, or the resistance in between the base and the emitter terminals, which is equals to Vt over Ib and beta over Gm. Okay, so let's go back to our emitter configuration again. So our so if I will expand this amplifier circuit, this is what I am going to have. I am going to have this resistance R pi that will appear over here, and then I am going to have this voltage control current source that is going to appear over here, again GMV pi. So this GMV pi again can be seen over here, which is equals to GM-VBE. GM is this, and this is that voltage that is controlling this current, right? VBE over here, which we are calling in this circuit as V pi. So that is why the voltage value of this current source is GM-V pi, or the current value of this, yeah, is GM-V pi. Okay. So the input resistance again Rn. So let's our first thing is again our input resistance Rn. Again, Rn is the resistance that you can find by looking into the input of the transistor in a specific common configuration model. Over here, if you look into the input of this amplifier circuit, you can see that our input resistance is equals to R pi, right? Input resistance is R pi. Our input voltage is equals to V pi over here. If I want to make a one-to-one correspondence with this circuit over here, right? So this was our input voltage, this was our input resistance, this was a voltage control voltage source. Over there, we know that our BJT amplifier can work as a voltage control current source. All right, so this is what we have. All right, so our Rn equals R pi, and secondly, our output resistance, the resistance looking at the output of the terminal, our R naught equals to Rc, the resistance that we have connected to convert this amplifier into a voltage amplifier. All right, so let me start with, so essentially we are going to go through the same process of writing down these voltage divider equations and finding out the open circuit voltage gain, the voltage gain of an amplifier with the load resistance attached, and finally the overall voltage gain of an amplifier. Okay, so the first thing first, so let me start with the finding out the open circuit voltage gain. Before finding out the open circuit voltage gain, let me write down these voltage divider equations. So if I will write down this voltage divider equation VI, right, so our VI will be equals to a V sig into R pi resistance over there, R pi plus signal resistance. Okay, so this is what we know. Then we also know that our input voltage over here is equals to V pi. All right. Similarly, we can also, so let's also see how the output voltage looks like. Our output voltage V naught here, right? So this is the output voltage V naught, right? So V naught is the current that is flowing in this branch, which is equals to, what is the current that is flowing in this branch? GMV pi. So we have this current that is flowing. Note down the direction of the current. Because of the direction of the current, our equation for this voltage would be I into R, right? So due to the direction of the current, our equation for the V naught is going to be minus GMV pi into RC. So this is the value of the output voltage. Okay, so let's find out now our open circuit voltage gain when RL is infinity. So right now we don't have any load resistance attached anyways. So when no load resistance is attached, it will be equals to V naught over Vi, the same V naught here and the same Vi here. So we can easily see from this equation, from this equation and this equation, V naught equals minus GM V pi RC over divided by Vi. Vi equals V pi. So V pi minus GM into RC. So this is equal, so this is the open circuit voltage gain. Okay, now let's find the voltage gain with the load resistance attached, with RL attached now, and RL will be attached in parallel to RC, right? So it will be attached across this RC resistance, right? We're going to have this RL attached over here like this. Okay, so when we are going to have an RL attached, we will see that our voltage gain AV will now become minus GM. RC will appear in parallel to RL. So this is the voltage gain of an amplifier with the load resistance attached. And the final gain that we are interested in is finding out the overall voltage gain, GV, which is equals to the output voltage V naught to the signal voltage. Again, V naught over V sig was equals to, okay, so you have V naught over Vi into Vi over V signal. Now we know that what is Vi over V signal? Okay, let's first do this V naught over Vi. We already know V naught over Vi, which is equals to minus GM RC in parallel with RL. Right, so this AV is also V naught over Vi with load resistance attached. So in terms of an overall voltage gain, V naught over Vi is minus GM RC in parallel with RL, and then multiplied by this product, Vi divided by V signal. Vi divided by V signal is coming from here. Just take this V sig over here. So Vi over V signal will be equals to R pi over R pi plus R signal. Okay, so this is the value of your overall voltage gain. Your overall voltage gain will be equals to minus R pi over R pi plus R signal multiplied by GM into RC in parallel with RL. This is the value of the overall voltage gain, right? So this is how you can very simply analyze any configuration of an amplifier using some basic principles of how to characterize any amplifier. So this is what we have done with a common emitter. Now what we are going to do is we are going to do one quick example, and then we will also discuss a slightly more complicated case of this common emitter configuration, where we will also attach a resistance at the emitter terminal. And then we will reevaluate our or rederive all of these gain equations. All right, so let's do one example now for this common emitter configuration. So our example for the common emitter configuration over here is, all right, so we have a common emitter amplifier which uses a bipolar junction transistor. Beta value is 100. It is biased at the collector current of 1 milliamperes and a collector resistance of 5 kilo ohms. Okay, and this is what we need to find. Let's start from here, and then we are going to come back to the rest of the problem. Okay, so find Rin, R naught, and AV naught. Okay, so let us start with Rin. What is the value of Rn that we just calculated? We saw that our value of the Rn equals R pi. Okay, so I am gonna say, okay, so this is good. Rn equals R pi. What is the value of R pi? If you remember, the last lecture we derived all of these values in a lot of detail. Right, so R pi equals beta over GM, or VT over IB, and the GM equals IC over VT. So we are gonna use all of these equations here. Let me go back. Okay, so Vn equals so Rn equals R pi. Let's do now our R pi equals beta over GM. Okay, so this is good. Let's first find out the value of GM. GM equals IC over thermal voltage. Collector current value is given 1 milliamperes. So 1 milliamperes divided by thermal voltage, 25 millivolts. Right, so if you are going to solve this, is it 1 milliamperes and 25 millivolts? The value of the GM gonna come out to be 40 milliamperes per volts. So this is the value of the GM that we can find. Now we can replace this value over here, and we already know the value of beta. So R pi equals beta is 100 divided by the value of GM, 40 milliamperes per volt. So our R pi is going to come out to be 2.5 kilo ohms. So our resistance, the input resistance, all right, our input resistance was equal to R pi, so it should be equals to 2.5 kilo ohms. Okay, so this is great. The second thing that we need to find out is R naught. Over here, R naught. Okay, so let's find out R naught. Again, going back to the same model that we just derived, we know that R naught equals RC. All right, so our R naught equals RC, and we know the value of RC, which is 5 kilo ohms. So this is our value of R naught. Okay, so that was quick and easy. The third thing that we want to find out is the open circuit voltage gain, which means that no load resistance is attached. So open circuit voltage gain that we want to find out, again going back to the model, what was the open circuit voltage gain? Minus GM RC. So I'm going to use this equation now. Open circuit voltage gain equals minus GM into RC. So it should be equals to minus GM is 40 milliamperes per volts multiplied by RC is 5 kilo ohms, right? So you can cancel this thing out, and then 40 multiplied by 5 is going to be minus 200 volts per volts. So this is a value of the open circuit voltage gain. Okay, great. So we ended up solving this first part where we want to find out the value of the input resistance, the output resistance, and the open circuit voltage gain. Now let's look at the second part of it. If the amplifier is fed with a signal source having a resistance of 5 kilo ohms and a load resistance of 5 kilo ohms is the same load resistance is attached to the output terminal. Now we want to find out the value of the voltage gain of an amplifier with the resistance attached and the overall voltage gain. Okay, so now we are given some more information about the circuit. We are provided information about the load resistance, which is 5 kilo ohms, and we are also provided information about the signal resistance, which is also 5 kilo ohms, interestingly. All right, so now we are interested in finding out the voltage gain of an amplifier. Again, AV was equals to V0 over VI with RL when the load resistance is attached, meaning that there is a load resistor there. All right, so we can look at the formula again, going back here. Where is it? Okay, so this is our equation for voltage gain with the load resistance attached, minus GM RC in parallel with RL. So I'm just going to directly use this. AV is minus GM RC in parallel with RL. Okay, so minus GM is again 40 milliamperes per volt. And what is the RC? RC value is 5 kilo ohms in parallel with load resistance, which is also 5K. So if you are going to solve this, minus 40 milliamperes per volt into 5K multiplied by 5K divided by 10K. If you're going to solve this, the value of the voltage gain that you're going to come out, or you're going to found, is going to be minus 100 volts per volts. So this is the voltage gain of this amplifier. Okay, the other thing that we want to find out is now the overall voltage gain, right? So the other thing that we want to find out is this value of GV, right? So now we are interested in finding out the value of GV. Okay, so let's find out the value of GV. Again, GV, let me just divide this slide into half. Okay, here now I'm going to use this formula. Minus R pi over R pi plus R sig GM RC in parallel with RL. Okay, so overall voltage gain equals minus R pi over R pi plus R sig multiplied by GM RC in parallel with RL. So we just calculated the value of GM RC in parallel with RL over here, right? So it was minus 100. So minus, what is the value of R pi? R pi was Rn, input resistance 2.5 kilo ohms. So 2.5K divided by 2.5K, signal resistance is, I guess, 5K. And multiply by GM RC in parallel with RL, we just find it out to be 100. Okay, so this will come out to be minus 2.5 divided by 7.5 into 100. Okay, so it will be 2 divided by 3. So if you're going to solve this, 2 divided by 3, 200 divided by 3, you're going to, the equation that you will end up finding out will be, sorry, it should be 1 by 3, not 2 by 3. 25, yeah, 25 divided by 75 should be 1 by 3. Okay, so it should come out to be minus 100 by 3 volts per volt. So your overall voltage gain is going to be minus 33.3 volts per volts. Okay, great. So this is the overall voltage gain value that we ended up finding. Okay, let's do the third part now of the same problem. Okay, so the third part says that if V pi is to be limited to 5 millivolts, meaning that if the input voltage, we know that Vi equals V pi here. So the input voltage, the swings or the changes in the input voltage, or the peak changes in the input voltage, is to be limited to 5 millivolts. What are the corresponding values of the output and the signal voltages that we ended up finding with the load connected? So let's figure this thing out. So we are given V pi to be 5 millivolts. Okay, so we know that our V pi is 5 millivolts, and we want to find out the value of the signal and the value of the output voltage. Okay, interestingly, so let's go back over here and see that we have our input voltage is equals to V pi, right? And if we will use this voltage divider equation, we can easily find out the value of signal, right? We know the resistances, R pi, R sig, and we know the value of Vi, which is V pi, so we can find out the value of V signal. Okay, so we can use this equation, Vi equals R pi over R pi plus R sig multiplied by V sig. So this was a voltage divider equation that we have seen at the input. So we can rearrange that to be V signal equals to Vi into R pi plus R signal divided by R pi. So our input voltage now VI is 5 millivolts. VI is V pi again, right? So it is 5 millivolts into R pi. R pi, we have seen that again, 2.5 kilo ohms R pi, and R signal is 5K. Okay, so we ended up getting 2.5K plus 5K divided by 2.5K. So if we can, so this will be 5 milli into 7.5 divided by 2.5. 5 milli multiplied by 3, so it comes out to be 15 millivolts. So our V signal will be limited to 15 millivolts. Now let's find out the value of V naught. We know that our overall voltage gain now equals V naught divided by V signal. So we can easily use this. V naught will be equals to voltage gain, overall voltage gain divided by V signal. So our V naught will be equals to our overall voltage gain is what was the minus 33 here. Minus 33.333 into V signal, which is 15 millivolts. So we wanted to know the changes, right? Okay, so it can be even plus. So the negative sign just indicates that we have our amplification over here is inverse. In terms of finding these values, V naught and the V6, we are interested in finding out the limiting values of these voltage signals that are allowed here. So 33.3 is the voltage, overall voltage gain, and we are going to multiply that with a V6, which is going to be 15 millivolts, so 0.015 volts. So our V naught is going to be, if you're going to multiply both of them, 0.5 volts. So this is going to be our output voltage of an amplifier when our V pi will be limited to 5 millivolts. Our V naught will be limited to 0.5 volts. Okay. Okay, so this is good. We ended up doing, okay, so let's do a slightly more complicated common emitter configuration model. And in this model, what we are doing is essentially the model is exactly the same, right? We have a common emitter thing here. What we ended up doing is now we have an emitter resistance as well. Now we have an RE emitter resistance attached here. Okay, well, most of the other things are the same, right? We have RC resistance attached at the output. This is our input resistance, this is our output resistance. So let's make an equivalent circuit model. When we make an equivalent circuit model, the model looks slightly different. Rather than using a hybrid pi model, this time we ended up using a T model, right? Again, showing you the T model over here. This was the T model where we had a base like this, collector like this, and emitter like this. And our resistance is the emitter resistance in between base and the emitter in a T model. Okay, so let's use the T model here. So when we use a T model here, right, you have a current source alpha times IE. The same emitter current is flowing through the circuit. You have a resistance RE here. This is this emitter resistance RE over here. Our R naught, our V naught value remains over here. First, we are going to consider that no load resistance is connected. Then we are also going to find out the equations with the load resistance attached. Okay. So let's solve this circuit. Let's find out our Rn is not going to be simply R pi like our previous example, because now we have an emitter resistance attached as well. Okay, so what is the input resistance that we can find it out? For example, if we look at this input resistance, right? So this input resistance, looking into the input of the amplifier circuit, we are going to have a VI voltage and a current IB. So I can also write Rn as input voltage divided by the base current. All right, now I have to find out these equations. In order to find out these equations, let's see. So this is the equation. All right. Now what else do we know? We know that the base current equals IC over beta. we also know that IC equals alpha times IE. So these are some of the equations that you have seen so many times by now. All right. Okay. So I have to find out this value of the input resistance, and I need a voltage VI and a base current IB. Now the first thing that I'm trying to find out is an equation or an expression for the base current IB. So one equation that we know for the base current is IC over beta, and the other expression that we know is alpha times IE. So what I'm going to do is I'm going to replace this IC over here. So my new value of the base current will come out to be alpha times IE over beta. Now we also know that beta equals alpha over 1 minus alpha. So considering that, I can rewrite this equation as, now I'm going to have alpha IE, putting down the value of beta, 1 minus alpha. So this is the equation that I got. Our base current equals to 1 minus alpha times IB. Similarly, we also know that, so you can use this thing as a one equation. Similarly, rather than using beta equals alpha over 1 minus alpha, we can also use the other expression, which is alpha equals beta over beta plus 1. If we use this expression and now put this value of alpha all the way here, then our base current will be equals to IB equals to beta over beta plus 1 into beta into IE. So the value we are going to get is IB equals to IE over beta plus 1. So our base current is going to be 1 plus beta IE. Okay, great. So this is the value of the base current that we ended up finding. Again, all of these equations, for example, IC over beta, alpha times IE, beta equals to alpha over 1 minus alpha, or alpha equals to beta over beta plus 1. All of these equations are coming from one of the very first few lectures of the bipolar junction transistor, right? We write all of these equations from there, right? For example, this one, this one, this one, this one. So that was, I think, first or the second lecture of the bipolar junction transistor. By now you should kind of remember those equations. We have used that so many times. Okay, so we ended up finding out the value of the base current, IB. So what I'm going to do now is I am going to put down this value of the current over there. All right. All right, so let's, even before doing that, let's look at the circuit again. And from the circuit, I can also write down the equation for IE. So equation for IE here, IE equals to VI over total resistance here, RE plus capital RE, small re plus capital RE. So this is the value of the emitter current. Now I can put this value of the emitter current over here to find out the new value of the base current. So the new value of the base current will be 1 plus beta times VI divided by IB equals VI, sorry, IB equals sorry, yeah, so I think this equation was wrong. So when our IB needs to be multiplied by 1 plus beta, yeah, so this should be, okay, let me run this thing. All right, beta plus 1 into beta, so this will be cancelled out. Our new value of IE now will be equals to IB into 1 plus beta. Now we can also see our emitter current equals VI over RE plus RE, Again, this is coming from this branch. And now we can put this value of the emitter current all the way over here to find out the new value of base current. IB equals VI divided by IB equals, okay, VI divided by RE plus capital RE into 1 plus beta. So this is the new value of the base current. Now we know that our input resistance equals over here VI over IB. So what is from here, we can kind of cross this thing. All right. So we can, from here, we can find the value of VI over IB. All right. So our VI Rn equals VI over IB, and that should be equals to VI over IB should be equals to RE plus RE into 1 plus beta. Okay, so this is the value of the resistance that we ended up finding. Okay, so our input resistance is RE plus RE into 1 plus beta. Okay, so interestingly, what we see from this equation is that the input resistance, let me write this thing down as well. Input resistance looking into the base is beta plus 1 times total resistance in the emitter. And this is known as resistance reflection rule. Okay, great. So what does this thing mean? So this thing means that if you look closely, your Rin is the resistance that is looking into the base, right? So this is Rin looking into the base. So our resistance looking into the base equals 1 plus beta times the total resistance that is appearing in the emitter branch, right? You have an RE plus RE. So this phenomenon is called as a resistance reflection rule. Okay, so we ended up finding out the value of the input resistance. Actually, this took a lot of time. Now I think our life is going to be slightly more simpler. We are going to perform the same process. So the first thing that we want to find out after finding out the value of resistance is the open circuit voltage gain. Again, open circuit voltage gain is when RL is infinite and V0 over VI. This is what we want to find out. So let's find out the value of the output voltage. Our output voltage should be from here. Our output voltage should be our collector current. Look at the direction of the collector current, right? So it should be IC RC, right? And our collector current is flowing in that direction, so our output voltage is going to be minus ICRC. And now we know the value of IC, which is alpha times IE, right? So this is alpha times IE. Okay, so we can replace this value over here. V0 equals minus alpha times IE RC. Now, we also know the value of IE that we initially determined in the last slide. Where's the value of IE? Okay, this is the value of IE. VI over, RE plus RE. So we're going to use this value. IE equals VI over RE plus RE. I'm going to use this value again over here. So our output voltage now equals to be minus alpha times VI over RE plus RE multiplied by RC. So our open loop voltage gain is going to be again minus alpha times RC over RE plus RE into VI. So our open loop voltage gain, which is equals to V0 over VI. So I have to move this VI on the other side. will be equals to minus alpha times RC over RE plus RE. So this is our open loop voltage gain that we can calculate. Okay, so another interesting thing. So after finding out the open loop voltage gain, the second thing that we can do is find out the value of voltage gain with the resistor attached. So let's do the value of the voltage gain. Again, V naught over Vi with load resistance. And again, our load resistance will be connected now, and that will be connected in parallel to RC. Note down that your R naught over here is equals to RC. Okay, so our R naught over here would be equals to RC. So if we look at the output of this amplifier circuit, it looks very similar to our main characterization of an amplifier, and we know that from our voltage gain of an amplifier equals AV naught RL over RL plus R naught. So we are going to use that equation. Where is that? Okay. So our AV equals AV naught RL over RL plus R naught. And we know the value of AV naught from here, which is equals to minus alpha times RC over RE plus RE multiplied by RL over RL plus R naught is RC. So this is the value. Another interesting thing that you can see actually from here is minus alpha over RE plus RE into RC RL plus RC, right? Our RC and RL are appearing in parallel over here. So we can also write the value of the voltage gain as minus alpha RE into RC in parallel with RL. Okay. So this is how we can find out the voltage gain of an amplifier of this common emitter configuration with emitter resistance. The last thing that we need to do now is to find out the overall voltage gain. Okay, great. So let's find out the overall voltage gain. We again, going back from this, we know that our overall voltage gain equals to, this is our AV, voltage gain of an amplifier, multiplied by Rn over Rn plus Rsig, right? Okay, so let's do this. Where is it? Okay, so we want to find out the value of the GV. So GV equals AV multiplied by Rn over Rn plus R signal. Okay, so let's find out this value now. Overall voltage gain. All right, so first thing first, where our Rn, what is the value of the input resistance? Where's the input resistance here? Not here. Okay, so this is the input resistance that we ended up finding. Re plus Re1 plus beta. Re plus Re1 plus beta. So this was the input resistance that we need. And then we are going to have a signal resistance and the value of the AV. So right now, all we need to do now is to replace this value AV over here and replace the value of Rn and then solve it. All right, so overall voltage gain, GV equals AV. The value of the AV again is going to be minus alpha RC in parallel with RL over RE plus RE. Let me cross check this. Okay, good. And then we are gonna have Rn over Rn plus R signal. All right. Again, minus alpha RC in parallel with RL over RE plus RE multiplied by, what is the input resistance? RE plus RE into 1 plus beta divided by Rn plus R sig. So Rn is Re plus Re plus, into 1 plus beta plus R signal. Okay, great. So we ended up crossing this out. And what we are left with is minus alpha into 1 plus beta into RC in parallel with RL divided by RE plus RE plus 1 plus beta plus R signal. Okay, so this is good. The only thing now that is left is another thing that we can we cross out the 1 plus beta from here? Probably there's no need to. Okay, so I think another thing that we can do is we can kind of replace this thing. We know that alpha equals beta over beta plus 1, so we can take it over there. Alpha times beta plus 1 equals beta. So this will be a more simpler expression. Our overall voltage gain is equals to minus beta RC in parallel with RL divided by RE plus RE 1 plus beta plus R signal. So this is the value of the overall voltage gain that we need for our common emitter configuration with the emitter resistance. Okay, great. So with that, this ends up our lecture today. And in the next lecture, what we are going to do is we have a couple of configurations left. We are going to do a common base configuration, and then we are going to do a common collector configuration, and we will do one more example in the next lecture, and that would be the last lecture for the semester. Again, thank you so much. Best wishes for you all. Thanks. Bye-bye.